Hello friends, I'm Sarita Verma and welcome to my channel Electronics Simplified. Today in this video we will talk about full wave rectifier. The contents are objectives, full wave rectifier, need, types of full wave rectifier, central tap full wave rectifier, operation, efficiency, ripple factor, advantages and disadvantages, application of full wave as well as central tap rectifier along with applications. This video has been designed with the objective that after observing this video, learners should be able to understand why a full wave rectifier is needed, how to define a full wave rectifier, describe the operation, draw its circuit, draw waveforms of full wave rectifier, calculate the efficiency and ripple factor, and list advantages, disadvantages, and applications, and of course, compare the different types of rectifiers. In my previous video of half-wave rectifier, we have already seen what is a rectifier. A rectifier is a circuit which converts AC to DC, and we have seen that the output of a rectifier contains both AC and DC component. The output is not pure DC. Hence, it contains ripples. So, ripple factor of half-wave rectifier is very high, 1.21. Efficiency of a half-wave rectifier is just 40.6% because it conducts current for only one cycle of the signal, and the remaining half cycle, the negative half cycles we can say are suppressed. Hence, we need a rectifier with better efficiency and less ripple factor. So, let us see what we mean by full wave rectifier. In full wave rectifier, current flows through the load in both the direction, in both the cycles in the same direction. Yes, we have two different types of rectifiers, central tap full wave rectifier and a bridge rectifier. To understand central tap full wave rectifier, let us see the circuit diagram of a central tap rectifier. This is the circuit diagram. And how is it different from your half-wave rectifier? Fine. Here, the AC supply which is to be rectified, which is to be converted from AC to DC, is given through a transformer. Here, the transformer is a central tap transformer. So, this is the primary winding and this is the secondary winding. The secondary winding is divided into two. Upper half of the secondary winding indicated by OA and the lower half of the secondary winding indicated by OB. These are the two diodes, D1 and D2. So, during the positive half cycle, you can see this end A becomes positive and the end B becomes negative. So, the result is this diode D1 will be forward biased and D2 will be reversed biased, and current will start flowing from the point A through the diode D1 through the load resistance RL. Whereas, no current will flow in the lower half of the secondary winding because the diode D2 is reversed biased. It acts as an open circuit, and the complete voltage, which is equal to Vm in the upper half and Vm in the lower half, maximum voltage, that will appear across the secondary winding D2. Is it clear to you? Same way. So, whatever input we apply during the positive half cycle, same will appear at the output and the diode D1 will be conducting. During the negative half cycle, reverse process will occur. End A will become negative and B will become positive. Result will be diode D2 will become forward biased, D1 will become reverse biased. So again, the complete voltage across the upper and lower half of the secondary winding will appear across the diode D1, that is twice the peak inverse voltage or twice Vm, we can say. Okay, twice Vm. And the current conduction will start taking place from from the terminal point B through the diode D2 and indicated by an arrow through the load resistance RL. So the output voltage will appear at the output in this form due to when the diode D2 conducts. We can see the direction of current for both the positive and negative half cycle through the load resistance is in the same direction. So this is the diagram illustrating the operation of a central tap rectifier. Same thing. Here you can see during the positive half cycle, diode D1 is switched on, D2 is switched off, and this will be the output across the rectifier. And similarly, when negative half cycle occurs, in that case the reverse will occur, but the direction of current is the same, so it will be shown in the same direction when diode D2 conducts. So now we have seen what is a central tap full wave rectifier, as well as what type of output waveform we will get across a full wave rectifier. Now let us see what is the efficiency for a full wave rectifier. For a half wave rectifier, we have already seen that efficiency, or eta, that is given by that is how much portion of the AC is converted into DC. So DC power output upon AC power input. Yes, if you remember, how much was IDC for a half wave rectifier? It was Im by pi. Clear? And here it is twice Im by pi, because in the upper half and the lower half of the second dividing. Similarly, IRMS is equal to Im by root 2. So rectifier efficiency is given by PDC by PAC, and eta can be calculated, that is the efficiency. Here RF is the load resistance. So what we find that efficiency for a central tap full wave rectifier is 81.2%. Here the diode resistance RF is negligible or very less compared to your load resistance RL. So efficiency of your central tap rectifier, we can say, is twice that of your half wave rectifier. If you remember, it was 40.6%. Here it is 81.2%. Similarly, measure of the purity of the DC output of a rectifier. As we remember, that output of rectifier contains both AC and DC component. Fine. So ripple factor is measured by the function, or we can say by using the symbol gamma, RMS value of the AC component of the output divided by the average value of the or DC component of the output. So ripple factor is given by IAC by IDC. So by substituting the values of IRMS and IDC in the formula for ripple factor under root of IRMS by IDC whole square minus 1, we can calculate the ripple factor as 0.48, which is much less than half wave rectifier. So there are certain advantages as well as disadvantages for a central tap rectifier. Efficiency is very high compared to your half wave rectifier. Large DC power output is obtained. Ripple factor is less, but there are certain disadvantages also, because the peak inverse voltage rating of the diode is much higher compared to your half wave rectifier, because it will be almost twice Vm. Because when the diode is reverse biased, the complete voltage which appears across the upper half and lower half of your secondary winding, right, that will appear across the diode which is reverse biased. Higher peak inverse diode voltages are larger in size and costly also, and cost of central tap transformer is also very high. So let us see now what is a bridge rectifier. So we need to eliminate the central tap rectifier, and in place of 2 diodes for a bridge rectifier, we will be using 4 diodes. So here you can see they are forming a bridge. The 2 anodes are common together and connected to ground, and the 2 cathodes are common together and they are connected across the load resistance RL. Fine, let us see the operation of a full wave bridge rectifier. So during the positive half cycle of the signal, D1 and D2 are forward biased, and D3 and D4 are reverse biased. So they will be in the off state, and current conduction will take place from this point through the diode D1 through the load resistance, and of course here from the diode D1 through the load resistance like this through the diode D4 and back to the other end of the circuit. Similarly, for the next cycle, when during the negative half cycle, we'll find that the diodes D3 and D4 are forward biased, and the diode D1 and D2 are reverse biased. So current conduction will take place in this fashion during the negative half cycle through this diode, through the load resistance, and then through diode D4 back to the other end of the supply, that is the negative end. If we see the output of a half-wave rectifier, whether it is a bridge rectifier or a central tap rectifier, this is the input waveform, the AC signal, and this is the output waveform for a full wave rectifier. This is for a bridge rectifier. Two diodes will conduct for the positive half cycle, and two diodes D1 and D2 we have indicated, and D3 and D4 for the next cycle. As far as the efficiency, frequency of a full wave rectifier is concerned, then output frequency of a full wave rectifier is double the input frequency. Only one cycle is complete here. Two cycles will be completed in one cycle of the input signal. So F out is equal to twice F in. Full wave bridge rectifier. Yes, it has many advantages. Need of central tap transformer, which is eliminated, which is bulky. Peak inverse voltage is 1/2 of that of the central tap circuit. So of diodes is reduced and output is twice than that of the central tap circuit. Disadvantages: requires 4 diodes. Internal resistance voltage drop is twice than that of the central tap circuit. So there are few advantages as well as few disadvantages. As far as applications are concerned, rectifier is used in regulated power supplies. It is used in electric welding machines. It is used in traction, rolling, stock, and 3-phase traction motors, used for running trains. It is used for modulation, demodulation, and voltage multipliers. Now, let us see one of the applications of a rectifier. Let us see the block diagram of a power supply, which will consist of course, your input signal, which is an AC signal, that will be given through a transformer to a rectifier. Of course, the output is pulsating DC, so we need to remove the AC component from the rectifier output. So we'll be using filters. With the help of filters, the output will be filtered out. And since a constant output voltage is needed from a regulated power supply, a voltage regulator circuit will be used. Now it's time for a reflection spot, a time to find out how much we have gained after watching this video. Okay, so take a pause and try to answer these questions, specially framed for you. And I would like you to think for a while and try to find a point of distinction for a half-wave rectifier or full-wave rectifier. In full wave, you need to consider central tap as well as bridge rectifier. So apart from these questions, pause for a minute and try to write the points of distinction for the both central tap, bridge rectifier and half-wave rectifier. I hope you have written few points. Just have a look at the few points which I have written as comparison for the two types of rectifiers, half wave and full wave, and full wave central tap and bridge. Thank you.